Alright, let's look at homework 2.1, which is another review problem from Thermal 1. This is a pump for a steam power plant used in our Rankine cycle. Let's begin by making a little sketch of our system. Here's our pump. We've got flow in and flow out across our system boundary. And Q would be defined in and work positive out. For a pump, though, in this case, it's adiabatic, so this is going to be 0, and our work will actually be, power will be negative, less than 0. Now, since we're talking about the input power for the pump, we'll report that as a positive value. Our quality at the inlet is 0, it's saturated liquid, and the pressure is given as 0.08 bar. The exit, the pressure is given as 2.5 bar. Label that here. Okay, let's begin with the first law. So we have dE CV dt equals Q dot minus W dot plus summation M dot I HI plus VI squared over 2 plus GZI minus summation M dot E HE plus VE squared over 2 plus GZE. And we'll make some assumptions here. We were told that it's adiabatic, so no heat transfer. We're going to assume no change in kinetic or potential, so those differences will, or those values will cancel out since they're the same, inlet and exit. We're assuming steady state. We can bring W to the other side of the equation, but before we do that, let's look at the continuity equation. So the mass of the control volume as a function of time, or the rate of change of mass as a function of time, equals summation M dot I minus summation M dot E. Steady state, so there's no accumulation of mass in the pump. We only have one inlet, so we have M dot 3 minus M dot 4, and this side of the equation is 0, so that equals 0, which means that M dot 3 equals M dot 4, so we can just call that M dot. So finally, putting these two equations together, we get that W dot equals M dot H inlet, which is H3, the inlet call H3, and the exit H4. Now the mass flow rate is 45 kilograms per second. H3 we can get from the tables with the quality and the pressure known. So in the tables, we can look at 0.08, go over to the enthalpy for saturated liquid, and we find it's 173.88. So let's write that down. It's going to be kilojoule per kilogram. Okay, so we need a value for our H4. Let's look at the saturated liquid approximation. So we're going to use the saturation tables to get a pretty good value of the enthalpy for compressed liquid. And so the saturated liquid approximation is H4 equals HF at the given temperature plus VF the given temperature times the pressure minus Psat at the given temperature. And for this case, the temperature in the pump doesn't change, so T3 is going to equal T4, and vice versa. So we'll evaluate that at state 3, which means that H4 equals HF at state 3, which is H3, plus VF at state 3, which is VF at 3, times P4, the pressure, minus saturation pressure at state 3, which is P3. So now we can calculate those values. H4 equals 173.88 kilojoule per kilogram, plus, if we go to the tables for the specific volume, we get 1.0084 times 10 to the minus 3, because it's been multiplied by 1,000 here in the table, cubic meters per kilogram. Times P4, which is, I'm going to put it in kPa so that the units will be consistent. So 250 kPa minus 8 kPa. Just turn this over a little bit. So 1 bar is 100 kPa. And I do that because 1 kPa meter cube per kilogram is equivalent to 1 kilojoule per kilogram. And that's because Pascal, 1 Pascal is equal to 1 Newton per meter squared. So I've got a Newton per meter squared times meter cubed, which is a Newton meter, which is a joule. And so this gives me kilojoules per kilogram. So then finally I can do the calculation there, and I'll get 174.124 kilojoule per kilogram. So don't forget to use kPa, or you can work out the units as shown here. And okay, then our last step is to find H4. What we found here is actually H4S. Back here. So our pump efficiency is going to equal the work ideal over work actual, or in this case power. And so I have m dot times H4S minus H3 over H4 minus H3. And then I'm trying to solve for H4 in this case. So H4 would equal, kind of rearrange some things, H3 plus H4S minus H3 divided by the pump efficiency. And so in this case I have 190, trying to find my H3. H3 is shown here, 173.88 plus my H4S is 174.124 minus, kind of out of room there, so I can stretch this out a bit, minus 173.88 divided by my efficiency, which I believe was 85% or 80%. And then my final step is to find the actual power for the pump. So the work for the pump would be m dot times H4 minus H3. And in this case, m dot times 174.185, and then my H3, which is 173.88.